Good evening, all, and welcome to the 12th INA session of 2025. Today evening, we have got an interesting talk by Dr. Sajan Kapil from IIT Guwahati on computer-aided process planning for offshore repair and refurbishment using WireArc additive manufacturing. Our chief guest for the day is Dr. A. Mathiazhagan, Professor and HOD, Department of Ship Technology, Cochin University of Science and Technology. And our session chair will be Dr. R. Sankarasubramanian, who is a senior scientist in Defense Materials Research Laboratory, Hyderabad. It's my pleasure now to introduce the chief guest of the day, Dr. Mathiazhagan. He has 30 years of professional experience and currently the professor and head of Department of Ship Technology. He has been in CUSAT since 1994 and also held administrative position as HOD from January 2019 to 22, and this is his second tenure as HOD. He has an MSc in Applied Sciences from Anna University, ME in Metallurgical Engineering from NIT Tiruchirappalli, and a PhD in Technology, Material Technology Interdisciplinary from Cochin University. And his areas of teaching are Material Science and Engineering, Marine Corrosion and Prevention, Joining Technology in Shipbuilding, Marine Pollution, Soft Skills for Engineers, Professional Ethics and Human Values. And his areas of interest are material technology, corrosion engineering, welding technology, failure analysis, nanocomposites, material testing and characterization, marine pollution and control, and environmental management. And he has introduced a course on marine corrosion and prevention for both UG and PG, and also a course on marine pollution and prevention. And he has done significant projects on cathodic protection for failure analysis of boiler components, and has involved in CSR projects worth 356 lakhs. And he has got 2 patents and has delivered various invited talks, maybe around, in various forums, he has delivered around 16 invited talks, supervised 8 PhD students, and numerous MTech students, and various professional accomplishments. Some of them has been the member of World Academy of Sciences, member of Executive Council of PTA, DOST, and member of Board of Examiners in Anna University, external member of Patent Committee for Innovation in Kerala University, and he has also coordinator for sitting in electrochemical lab, member of Bureau of Indian Standards. There are various these things around like this. He has done around 38 various achievements, and also as HOD during 2019 to 22, he has introduced the outcome-based education in the department for naval architecture and shipbuilding, as well as MTech and CASAD, and department modelization, and implemented an NBA accreditation process and NASA accreditation process, and MOU between CUSAT and St. Petersburg State University in Russia. These were his achievements. And he has organized around 6 conferences and also published 2 books in marine corrosion and prevention and corrosion of ship steel structures, and numerous publications to list hundreds of journals as well as conference publications. It's a pleasure to have you to be the session chair for this session, sir. Welcome for this session, sir. It's also my pleasure to introduce the session chair for today. I will introduce the chief guest. The session chair is Dr. R. Sankarasubramanian. He is currently serving as Scientist G in Defense Metallurgical Research Laboratory, Hyderabad, heading the modeling and simulation group in the laboratory. He has his physics graduation from Madurai Kamaraj University, post-graduation in metallurgy from IISc, and PhD also from IISc Bengaluru, and did his postdoc in Institute of Physics, University of Augsburg, Germany, and then he joined DMRL DRDO. His research interests are in integrated computational materials engineering, multi-skills material modeling, density functional theory, molecular dynamics, Monte Carlo, phase fail simulations, and computational thermodynamics. And he has primarily applied these techniques for nickel-based superalloys. And he has served as the editorial board of transactions of Indian Institute of Metals, and also reviewer for several international journals. As his awards and honors are, he was a gold medalist in ME at ISC, Shriram Arora Award from the Minerals, Metals and Materials Society USA, and DRDO National Science Day Award. With this, it was my pleasure to introduce both the chief guest and the session chair. Now I'll hand over the session to the session chairman, sir. Please, sir.
Good evening, everybody. My pleasure to be the session chair for this session. I have some significant delay because of some network connection, so please bear with me. And today we have assembled to present from Professor Sajan Kapil on computer-aided process planning for offshore repair and refurbishment using WireArc additive manufacturing. It is my pleasure to introduce Dr. Kapil. Dr. Kapil is an assistant professor of mechanical engineering at IIT Guwahati and assistant project director TAH IIT Guwahati. He earned his PhD from IIT Bombay and MTech degrees from IIT Guwahati and the University of Stuttgart, Germany. He has held research exchanges at Washington State University, Fraunhofer IWS, RWTH Aachen, and Gifu University. He leads the additive manufacturing lab, AM lab, with research and interest in WireArc additive manufacturing, hybrid manufacturing, CAPP, and CAD/CAM integration. Dr. Kapil has published more than 60 peer-reviewed papers, holds 25 patents, and executed 20 plus sponsored and consultative projects. His translational initiatives include developing mobile WireArc additive manufacturing facilities, multi-material DED frameworks, and establishing India's first underwater welding certification program. He has also advanced offshore applications such as propeller repair through additive manufacturing and hybrid techniques, supporting marine MRO needs. Today, he will be educating us about computer-aided process planning for offshore repair and refurbishment using WireArc additive manufacturing. So I will hand over the session to Professor Sajan Kapil. Over to you, Professor Kapil.
Thank you very much, sir, for the introduction. Let me share my screen. I hope my screen is visible.
Yes, sir. So if you can change it to slideshow, yeah, perfect.
Yeah. So thank you. Thank you for the introduction, sir, and thank you, Anger sir, for inviting me for this talk. My name is Sajan Kapil, and I've already been introduced, but briefly I'll tell. For contact, if you want to make any contact or discuss anything, this is my email ID, and you can visit our lab, which is called amlab.in, which is under development, but many of the informations are available on the website. So I'll be talking about computer-aided process planning, particularly focusing on the offshore repair and refurbishment using WireArc additive manufacturing. In this particular talk, I'll be going through first introduction to additive manufacturing, which will be very, very brief, so that we are on the same page when I say a few terminologies. And then after that, it will be more focused on underwater application. That will be the today's goal. So I'll start with this video, which I typically do. These are the birds, they known as swiftlets. These birds are building their nests. They are using their saliva to deposit material. So like an unconventional way of building nest, the conventional way of building nest like other birds do, these birds are utilizing the method of additive manufacturing. This is 3D printing, where you are using any base, which may be a straight base or slanted base. Like here in this case, it is a cave, which is not straight but slanted. And then they are building their nest onto that. What does it require? Of course, the material is known to these birds. The requirement is the skill to deposit material and where to deposit, how much to deposit, so they get the shape. This is, in modern world, may be called as computer-aided process planning. If these birds are replaced by the robotic arms and these materials are being replaced by some other material, let's say metal. We choose additive manufacturing. This is a classical example of additive manufacturing in nature, but we do not really promote to pursue anything and everything by 3D printing in our lab. And this is another example. This is an example where the water leaves the limestone cave. It falls from the roof and it falls onto the a roof of the cave. When it does so, it leaves two material behind. One on the top, that means on the roof, another on the base, I mean the floor. These two material deposition keep growing, and they meet. And that's why in the caves you see those column-like structures. These column-like structures are not made by removing material. That means the water did not cut by its flow the excess material and give the shape to these columns. No, they are deposited. These structures you can't really get by conventional removing material. You have to go with 3D printing. But there's a challenge. I mean, growth of this particular structure is a few micron in a year. And that's how typically 3D printing does, right? It's sometimes expensive, sometimes very time consuming, sometimes it can't handle material. So keeping all that in mind, we always recommend a combination of additive, subtractive, or and other conventional manufacturing processes also in mind. So with that brief introduction of additive manufacturing in nature, now I'll jump to the additive manufacturing. What is it? It is typically known with many names. I'm very sure you might have heard one of these names. 3D printing, stereolithography, layer manufacturing, additive layer manufacturing, additive digital manufacturing, additive manufacturing, layer-based manufacturing, layer-oriented manufacturing, solid free-form fabrication, digital manufacturing, rapid prototyping, rapid manufacturing, So all these names typically are given to this technology and have some reason for that. And maybe in the end of the talk, I'll mention about where you can know more about 3D printing. Particularly if you want to learn in detail. But over the period of time, additive manufacturing was the more adopted name by the scientific community. How does it work? 3D printing or additive manufacturing? It works in 3 steps. Pre-processing, where you get the CAD model, convert it to STL files sometimes you don't, and then do the slicing. Slicing can be like this planar slicing, or it can be like conformal slicing like onion or like cabbage, So everything is covered one over another, not in a linear fashion. So this particular part is called pre-processing because you are not making part here. Then you add material. And of course, there are 3 different possibilities when you add material. You get nice base at the center, but when you are depositing at the edges, it depends. If it is, too much overhang, then it will roll away the material. If it is not, it will held by the surface tension. It will not let it fall. The surface tension, but the surface tension may not, control a lot of gravity. If too much of the material is outside the edge, it will definitely roll over. So you need support structures, all that to be planned, during the pre-processing phase only. Then we build material. Now, how do we build material? How do we, build parts or add material? There are 7 different ways of adding material as defined by ASTM. This is classical classification, but nowadays, few more new methods are coming up. So I'm sure, like our manufacturing process, we call something conventional manufacturing and then unconventional. So maybe after 5-6 years, you will hear unconventional additive manufacturing also. But conventionally, I mean, till now, we have 7 methods of adding material. What are those methods? I'll briefly tell. They depends on what is the physics behind adding the material. Like the first is wet photopolymerization. As the name suggests, there may be a wet UV light falls into it. It makes sure that the material get cured and joined together. So polymerization, wet photopolymerization. The material is getting added by polymerization. The second is material jetting. That means you are jetting the material and somehow it is getting stick to the base and further layers. It is just like your color printer. In color printer, you inject the material. That material got stick to the paper. And if you keep doing so, you will have the part ready. Correct. The third process is the binder jetting. That's obvious method, right? As the name suggests, in this method, what you do is spread layer of powder, and wherever the binder falls, the binder can be, just like liquid, just a water as well. I mean, assume that you have spread a layer of sugar, and wherever the water falls, what will happen to that particular dot? It will become hardened, right? Or it will cure, or it will get bond with the nearby particle with some mechanism. The fourth method is material extrusion. Extrusion, we all know what is extrusion. Extrusion is a process in which we push the material from a larger orifice or larger area to a smaller area. Making jalebi is an extrusion process, right? I mean, the process in which we press and then, extrude. There are other extrusion processes you might have seen, making chakli and all, right? So in a similar fashion, but here the material should be in a form that when it deposit, it get collected. Now, I mean, of course, if you just put it directly, then it is not an extrusion process. What are the process follows into that? Concrete printing, you might have seen. They put a large amount of slurry on top, and then the slurry is extruded through a tiny pipe, a small pipe, smaller than, of course, the reservoir, and the material is extruded and then deposited onto the desired portions. Or it can be FDM, you might have heard, the 3D printer, plastic printer, which works with the wire. The wire comes and goes through a liquefier. Liquefier means just like a heater, which heat ups that wire and get melted, and then the wire comes out through a tiny orifice, and then it deposited onto the layer by layer fashion. So material extrusion is that process in general. I mean, the method is material extrusion. Then comes the sheet lamination. As the name suggests, in this case, you take the sheets and then you keep adding those sheets together. Assume that you have sellotape in your hand and you keep adding sellotape one over another, you will have the part ready, right? Or otherwise, it can be the powder bed fusion. The powder bed fusion is, of course, as the name suggests, you spread a layer of powder, and the particle need to be fused with the, the pre-deposited layers or the bed. And the last one is called directed energy deposition, the seventh process, in which we direct the energy towards a target and you feed material there. Now, in summary, I'll show you some of these processes here. Like I said, this is the wet photopolymerization, right? Here you are giving light from the bottom, and that light makes sure that the material is getting deposited, onto the layers. This one on the right side is powder bed fusion, in which you see a layer of powder and the laser writes over that powder bed. Wherever the powder that laser falls, that portion of the powder bed get fused. Or it can be the process like this, the material extrusion, where I already mentioned the wire is coming, that is getting melted and extruded through a tiny orifice, and you keep collecting the deposited material. But the bottom two are called the DED, directed energy deposition. As we are today talking about ship, right? The large scale structures, obviously, and metallic, right? Most of the things are metallic. I'm not going to, the FRP or the composites. I'll be mostly talking about the metals. But of course, if required, maybe some other time, we can talk about utilization of 3D printers to fabricate the large scale plastic parts as well. But today's focus is on metal. So this is the process which you see on the bottom side. DED, directed energy deposition, is the most suitable process for that. Because here you don't have a limitation of, for example, in powder bed fusion, you have a limitation of how large you can spread. And you can imagine, assume that I'm spreading a very large bed of powder, which is 40 micron thin. And assume that I want to spread it on a, let's say, 1 kilometer area, or let's reduce to maybe 50 meter, which is not very large for DED, or maybe 1 meter. It is very, very difficult. I mean, 40 micron uniform spreading itself is a nightmare. And then, of course, there are other challenges coming up. While in DED, assume that this welding gun, which is just depositing this cylinder, right? What if I put it on a truck? I mean, on a robotic arm, and just deposit one location, move to the next location, deposit next location, go to the next location. I mean, there's no limitation on the size in this process. Particularly on the right side one, where you have welding guns in your hand. Not on the left. Of course, there are issues with the powder also. I mean, handling powder in open environment is another challenge. But this DED process, which uses, welding guns, has a lot of potential. It looks like just a welding process, a welding gun mounted on a robotic arm, but it requires, of course, now, as I already said, welding guns are there, robotic arms are there in market. Now, what are we doing? We either do the material analysis, we find the right material, or if the material is existing, for example, in the shipbuilding or maybe in construction industry, mild steel is a very well-known material and weldable material. So the expertise required is for computer-aided process planning. That how do I plan my deposition process so that I can build structures. And that is not an easy task, because here there are a lot of challenges on CAD and CAM. I'll explain through my presentation. You can control even a lot of material properties through this. Just planning the path. Now, is it new? I mean, what I'm talking about, is it like a patentable thing? No, definitely not. It is a very old technology. You see the first patent filed on this invention. Somebody came up with the idea of why don't we use welding gun and keep depositing and let's make something. But then it may not be an engineered product. I know it will be something like a decorative item. Chalo, maan lete. But once you replace those hands with the robotic arm and the welding gun with a very sophisticated welding gun, then it becomes WireArc additive manufacturing. But the idea remains same, right? So I don't think there are many IPs in the process. Of course, there are IPs and there are many other different aspects. But on the process, it was very well open 3D printing process. You can see the first patent of 1920. And some of you, always, I faced this challenge because I made my first propeller when I was in IIT Bombay working with Professor Karunakaran sir. I see that challenge in industry when we try to build something. There was a hesitation in accepting those parts because they think it's weldable. Welding is not good. So we that time used to argue that okay, if you have even single weld, that property will keep propagating. If that weld doesn't work, that means the whole thing, if you even make by welding, will work. So I mean, but it was difficult to mitigate those challenges. But today, if you have any doubt, let me first show this so that those questions will not come. This is a large part. It's a 5-story building part approximately by Reality Space, I guess. And this YouTube channel is Veritasium. Veritasium is a very innovative YouTube channel. They keep uploading, the innovative ideas of what's going on technology. So this whole, this is just one part of it, was built by a welding gun only. Welding gun, switch it on, keep building a 5-story part. And this part is already in space. I don't think many of the applications are more critical than this. So we have to work together. Of course, there'll be requirement of metallurgists. There'll be requirement of people like us, the mechanical engineers, trying to plan the process and deposit material efficiently, and of course test it, provide the report and all the mechanical testing. But it is doable. If the things made by this technology are in space, then definitely they can be for other applications also. It's just the right material selection and some analysis in that direction. What we do plan, we do path planning. So this is the main topic of today, which is not much popular in additive manufacturing community in India, because this is typically be considered as the job of the machine provider maybe, but it changes a lot of even metallurgical aspects, even the outcomes, efficiency, a lot of things. I'll show you. Being I'm not a metallurgist, I'll show you how we tweak with these patterns of scanning and we get different results. Now, how do you take this analogy? Assume that you got a tractor, you are in a field. The way you scan the field to put the crops, the seeds, and then the yield can change. It depends on a lot of factors. The wind coming from which direction in this season or something like this, right? How the water will go, right? Water will flow. So all that can be heavily affected by the guy who came just for planning that how do I'm going to put the seeds. So that's the call the planning. I mean that's the way, the how, in which sequence, how do I deposit material. And this is called tool path in our case, which I'll very often say. So you just consider that you got a welding gun, and I'll decide when to deposit where, how much to deposit, to control its microstructure, to control its mechanical properties. So I'll directly start with a very important tool path, because I'll again not go very deep into tool path. We usually go into then math level of it, the CAD part of it. I mean, okay, how do I generate interesting tool path? What's the math behind that? And then algorithms for that. I'll not go into that, but I'll show you one very interesting tool path which gives me very interesting results. It's called trachodal tool path. Trachodal, I mean, it's again a very new, not very new thing. People have tried trachodal, this path, but in machining typically, not in 3D printing a lot. I'm not saying it was not tried. Of course, this is a well-known path in mathematics. So how does it work? Instead of depositing, if I want to deposit material inside these, I will not just deposit circular, one circle then another circle, not like this. Instead, I'll deposit like jalebi. You see this? And of course, we did not inspire by jalebi. This is an analogy which I am showing you now. But what are the benefits I'm getting when I deposit with this, at least the mild steel, the grade which I have, and this is the published paper, that I was able to penetrate more into the base metal. And why can't I do that when I go single? I mean, just a single track, because you deposit less amount of material above the substrate if you just go straight. But if I keep going like this, I can deposit a lot material, 6-7 thick material with the same wire. The penetration is even more. And due to that, what happens? The penetration improves, but the percentage dilution remains same. Because I'm 5 mm above, 1 mm below. What if I am, let's say I divide by 10, I'm 0.1 inside and 0.5 above, but still that penetration is 0.1. That depends how much you are holding, right? How much you are holding the hand in this direction, just the analogy. And when we did that, we find very interesting results. We saw that the strength, if you observe here, I mean, sorry, this is the elongation. This is the strength, the ultimate tensile strength. It is nearly, same. In the build direction, it is even more, interestingly. Of course, this is because we are penetrating a bit more. And this was, a very interesting results that typically we think 3D printed parts are not strong in build direction, but not really. If you plan just the path accordingly, you see. And not only that, I mean, the part deposited by this were quite homogeneous in the microstructure. We were struggling to find has, which is a very common, zone in welded parts. Those are called the heat affected zones. Then it was very difficult. You can see that the sample, which has been a very tall wall, and then we took a sample out of that in this region, and then some coarser microstructure in this zone, but not very clearly visible. And how we did that? Just by changing the path. I mean, the way we are printing the material. Now, I'll again go back to the analogy of my the jalebi making. Of course, you think why we can't just deposit jalebi like this? I mean, we will deposit the same amount, but there are reasons. I mean, you can print net shape and then break it. So this path affects a lot of things inside the metallurgy and the mechanical properties. Not only that, then the challenge comes when you meet, more, make more friends of metallurgists, and then their requirements, their imaginations are even much more, right? So one of my friend, when we discuss, we want to build materials, those vary like this, as you see in this image. And I'll not talk about Z direction variation. I'll talk a bit. Assume that you want to deposit a material which is red on the bottom and then blue on the top. Can you really identify a location where this nice picture has changed from orange to blue? It's nice continuous gradient. Or can I, for example, deposit material with different microstructure at the desirable location? I mean, of course, I can build the part, then you put in a furnace, and then you do the heat treatment, you'll get the desirable microstructure. But can I build a part in which I have some desirable microstructure here, something there, something there, something? I mean, imagine what kind of heat treatment will be required. But I can do that with toolpath. I can plan how much heat to be provided at this location, when to stop my welding gun, and how do I cool it down. Those cooling curves I can engineer while depositing material, and I can assure that it will give you right mechanical or microstructure requirements. This is monolithic material, single material, but just by changing, tweaking that path, I'm able to control the microstructure. Here you see this portion is rich with the conventional microstructure, where you have, I mean, when you deposit conventional, when I say it means when you deposit mild steel by 3D printing, typically you see perlite, ferrite. But if you do some tweak with the path planning, you see this region, this is rich with benite. And this is only mild steel, because then again, like I said, I need more material experts to discuss. I mean, if they have some ideas that, okay, what if we, can you vary the microstructure in this particular alloy? So we can try, we can work out. So it's like a reverse engineering from a metallurgist, providing metallurgist being a doctor, assuming they are giving me prescription. And that's like, I want this microstructure at this at this location, and these are the cooling rates. Can you plan the path in a way that, I can get the desirable outcome? So this is one. Another one is the engineered porosity. Of course, the porous parts are not a new thing, but the pores are close. Open pores are easy to make. We know that, foams and all, but that closed pores in metal, but challenging. And those two engineered pores, right? See these two blocks. One on the left side, which is weighing 475 gram, and the right side one weighing around 520 gram. The weight is different, but the shape is exactly same. There is no difference in size of these two blocks. And we could do that. I'll just very quickly move, because I don't know. Amir, please remind me when I am at least having 5 more minutes.
Sure,
I mean, 5 minutes. Please, thank you. So, for example, I deposited a layer. Then I can make tiny holes into that. Now, if the size of these holes is lesser than a certain value, the material will not go inside. You know why? Because of the porosity, the surface tension. Each molten material at a particular temperature have a certain viscosity. And it's quite viscous, of course, if it is to, very low temperature, and it doesn't flow at all, right? At room temperature, the mild steel. But even if it is molten and at a particular temperature, in welding also, it does not go into these pores for some process parameter. Of course, we can control the temperature. So that's why I said temperature. I mean, that depends on many of the current, welding, voltage, and many other parameters also. But those are my input, not the temperature. So I can cover these holes without let the material go inside. Now, this is an impossible part. You can't make it by powder bed fusion. Powder bed fusion, if you try any other process, the material will remain inside. And how you do it with casting, forging, you just forget about that. I have no idea what is the application of this. So, like being an academician, we do some imaginary work also sometimes, but why not in future, if some this kind of engineered hole inside the parts, may be required. How do I vary material? So density I can vary. You have seen, I can vary density. I can make it very heavy on this side, very light on that side, wherever you want. And you can't see that from outside. Outside, it will be nicely covered and without affecting its strength. Because typically, if you cover, sorry for this, just hold on. I'm sorry. Yeah. So we can vary microstructure. We have seen that given a cooling curve, I can control, my heat input at each location, and I can control the microstructure. I can control density. I can make part very heavy at one end, very light at one end. Can I vary composition? And why not? So this was our Indo-German project. IGSTC funded that. And in this, what we did, we used this plasma welding instead of MIG welding, in which we generate plasma at this location and we feed multiple wires from side. Now, these wires, I can change their speeds at desirable location. Unlike powder, I can do that in powder also, but it takes time and it's not really controllable by a programmer. I mean, you can define for a one layer, but if you want to change it very quickly, no, you can't program it. I mean, it's very difficult to program in one layer. You can do it in multi-layer. I mean, you can switch, let some powder get waste, then deposit, something like this. But wire is solid thing, right? You can absolutely control at a time t. That's important, huh? If I said at 0.1 second, this wire should be started, it will start. But powder takes time, right? So see this video on the right side. It's just increasing the programming capability now. You see, to the left side, I'm feeding P91, right side, I'm feeding mild steel. And I can vary these compositions on the go. Now, sky's the limit. I can build walls with different composition, mild steel, 50-20, some variation in between, like 80-20, 60-40, 40-60. Of course, this is easy. I agree, because this is not really a new thing, because in powder also people are doing so for so many years. But can you do that? This is in XY plane, changing the composition, starting from low carbon steel, and at this corner, it is 100% low carbon steel. 0% low carbon steel here. In between, you give me the curve. You want like 50-50 at center, fine. Or anything. Because in my CAD programming, I am now including the material information at each location. If I give you a task, I mean, the audience, if you know, if I ask, maybe you can think, you can make a CAD file in SolidWorks, right? Or somewhere. But can you give material properties to that CAD file different at different location, not on only surface? And those are all BRAPs, right? Boundary representations. But I want that composition to vary inside also. This software will fail. Of course, I'm not saying there are no schemes. There are schemes to do that. Maybe voxel representation, and there are many more. Computation is very expensive. The conventional computers may not even handle that, you know. But we can deposit. And I can vary those compositions in 3D. I need to just provide that X, Y, Z, the location where my gun is. Of course, the angle of the robot, I, J, K, comma, wire 1, wire 2, speed. That's it. I can control that. So this, the whole environment is in a virtual environment. That's what we do. Like I said, path planning or the computer process planning. I'll now go through some case studies, and that's where I think today's interest lies. Very quickly, we did one case study for automobile. This is an aluminum part we made. It looks like this after deposition, looks very bad. But then after machining, we got the final part. It was a big part. You see this, around 3.8 kg. It required a lot of machining. We deposited well. We got a good feedback, but I recently received a feedback that there are some issues with the holes, but not with the deposited. But because we are not an expert of machining, so I think some holes or machining issues are there. I recently heard, but earlier I came to know that it was very well made. We saved a lot of material, and they are trying it again to deposit, through warm. And then because they save a lot of material, otherwise they would have, you can imagine how much material they would have wasted. And this is aluminium, much difficult alloy to deposit. Mild steel is very easy as compared to this, because it gives you a lot of porosities, many such defects. This was my PhD work. It is not of IIT Bombay. This work I did at IIT not at IIT Guwahati. I did it in my PhD. So what video you are going to see is of 2014 when I was working with Professor Karunagan at IIT Bombay. So you can see I have retrofitted my welding gun on a 5-axis CNC machine, and then I deposited material. And again, the path planning was the only focus here, because realizing geometries at that time was quite challenging. Now, of course, all these companies and all these methods came up now, but this part was made in 2014, and I made, I think, 5-6 of them. So this is the most successful one. This is the deposited part, and then after finishing, this was my PhD. I also involved in building this part, where very interesting case study. I mean, how to plan depositing this part also by 3D printing. It requires in multiple settings, like setting 1, setting 2, setting 3, setting 4, in multiple settings, deposition, and then of course milling, and then you get the final part. That's how it looks like. This is another interesting case for a pin, which this is the pin which keeps breaking at this location. And I'm not sure, I would love to hear if somebody gives me a recommendation, or I can use it somewhere else also. But one of my students, Satish, he did a very good work on making metal matrix composites. Metal matrix composites are not easy to fabricate with the proper fusion with the fiber, and not over fusion with the fiber. Absolutely placing the fiber at the desired location is not an easy task. So what he does, he put the fiber of a tungsten and then deposit mild steel onto that. And he found a very good metallurgical bonding. Of course, it took him 2-3 years to do that, but very extensive research he performed. One of the very best work from our lab. And we used it for making some pins. Those were keep breaking, but then we put the tungsten fiber, it never breaks them. Of course, high temperature properties are even much beyond our expectations. One of the applications we thought could be nuclear, because these firing pins can absorb, the radiation. So, but we are still looking for a few more applications. This is one, of course, ongoing one. This is working. I can also control, I'll show you how I can control, the deposition while depositing material, the microstructure growth. Like I can deposit another one now, the drop. So this sequence of drop, I can keep controlling over the period of time, so that my cooling rate gives me, okay, now if I deposit another, the microstructure will retain. So I can engineer those cooling curves here. This was one part I made again in IIT Bombay during my PhD. This is the part for PHL Haridwar, made in 2015, a turbine blade. The shape was then objective. Of course, that time there were many. I mean, we find it very difficult to make them convinced that it is also possible. But I hope now they are also trying to explore 3D printing, particular DET for making turbine blades, because definitely it's better than casting. This is the case study at IIT Guwahati we are doing right now. We have got a case from mining industry. It's a huge die. It's around 600 kg, I believe. And a small portion of that got worn out, this portion. It's around 30 kg only. We scanned it already. We found a suitable material. It's a high magnesia alloy. And that's where I need my metallurgist friend to help me in identifying which material I can deposit onto that. So we provided them a lot of samples with different material deposited, and they finalized the material that wished to be deposited 30 kg only, and this die will be back to life. We'll send it back by depositing a different material, not the main material. This is a crusher, stone crusher, actually got worn out. When I said repair, then repair doesn't come with a known shape. It can get repaired then from anywhere. So we need a path planning which can even deposit, like this, like you see here. Here the deposition is happening vertically. I mean, not like this, correct? I can even deposit upside down, and the material will not fall by drops. So we have those path planning again. If you try to do this continuously, it won't work. One of the open challenge we used to give this, can you close the hole without putting a backup plate? And repair is, like I said, is the most important part. So how much to deposit so that it sustains? It does not conduct much heat. Otherwise, it will flow like honey if you just continuously keep depositing. and we closed. So it's a very quick solution for depositing. Otherwise, what you would have done, you would have make a cut, put it there, do the weld, right? And it requires a lot of time. Of course, here path planning may take time. Come in. I'm busy. Come after. Further path. 15 minutes. 15. The other one is the case we recently did for a space company. Again, in this case, you see we are depositing material, and it's inconel. Inconel is very difficult to handle because its conductivity is very, very low. And if the conductivity is low, what happened? It sustains that heat. It does not conduct that heat, and that will become a nightmare for giving a shape because it flow like again honey. If you just continuously deposit. So we have to take a pause, but when to pause, how to pause, so that desirable microstructure can be achieved. We did that. Deposit and give it to them. They are testing it right now. There are some, we thought like if we put tungsten, there may be an application in nuclear, but till now I could not reach to the right, I think, industry where I can propose this, like I can put tungsten into the wall because tungsten absorb radiation. But I can give shape also to that tungsten. I can make circular cylinder, which has 40% loading of tungsten in mild steel. It will be strong as well as maybe absorbing nuclear, but maybe some other applications as well. Happy to hear if you suggest something. You see this wall? These dots are tungsten fibers, and this is only 12%. We recently going to publish one more paper on how to load 40% tungsten into the mild steel. Of course, one interesting case came, but I have not started working on that. I don't know from where, but they want titanium fiber into aluminium. So I know it will require some inert chamber and all. So I'm working on that. But that could be the next metal matrix composite by 3D printing and the planning. You can't really just put it and then deposit. It won't sustain it. It will break. There are a lot of issues. So path and appropriate planning has to be done for placing those fibers. Now the water. So one of the mandate for my Indo-German project was to build something for underwater application. But it's a myth. Of course, underwater is not explored much, right? And we don't know whether part built by 3D printing will sustain or not. So we built a part. It was an electronic housing kind of a part. We gave it to NIO Goa. I'm very thankful to them. They test it. They put it in a pressurized chamber and they find no leakage. I think they put up to 100-meter depth, equivalent to 100-meter or 200-meter depth pressure. Now I'm trying to build another part, which will I'll try to send maybe to Chennai. They were kind. They said that when you are ready, I'll send them. They will also test it for maybe a more depth, maybe up to 1 kilometer or 900 meter, whatever facility they have, but it doesn't leak. So this gives us, of course, I'm not putting a lot of analysis here because I just want to show the final product result. But of course, we can discuss once it is failing, that how it is failing, the fractography of that and all. This is an interesting case on the right side. From Japan, they want us to repair a plate which is of 90s, 70s through this technique without removing the rust. And we did that. We find again a path. If we deposit by that path, it just pushes the molten material towards, because molten material, the rusted portion, because rusting is a lighter weight material in this case, right? Particularly in mild steel. The rust is lighter. When you deposit, float up. But if you push it away, you can see here, these are 3 beads. We keep pushing it from this edge towards this. And without anything, by removing the material, you can repair these sheets. And I don't know, but maybe in future we'll use it. We made this crane hook also by 3D printing. Then I realized we should do a proper study. And I'm very thankful to my industry partners, Saraswati Metal Works. They agreed to give me one propeller. They made a deliberate cut. They made 3 cuts. One like this, another 90-degree band. Our third one, they just to reduce the thickness. A lot thickness they have reduced actually from this portion. It's a bronze alloy. We took a task. We started with planning it. Of course, there are a lot of planning on how to fill this sharp edge, how to deposit this sharp edge, and then finally we can deposit. But I'm not the new. Rotterdam already did that. They call it warm peller. Of course, these are all images from them. Inspiration came from them. But fabricating a propeller, when I suggested to my industry partner, he said, Sajan, right now bronze is 900 rupees kg for casting hardly. Your wire is very expensive. And of course, it's not expensive because the material is expensive. Because it's expensive, there is no requirement. So the manufacturers are not making in that bulk quantity right now. We are importing this. If we make it in India, of course, it will be very cheap. The wire making is not a difficult for this. It's a easily drawable material. So we took a chance, okay, hai, let's not make the entire propeller, but we want to repair. But these are some other applications I find online through scientific papers and articles. Have people already done by warm in offshore. In offshore, they put welding gun on a robotic arm, deposit material, and they can get it done. So, of course, the first task was selection of material because the composition of base material was having quite of a zinc, right? You see that? But zinc is difficult to handle, it evaporates, there are a lot of issues, right? So we choose that copper silicon is not a suitable material because it lacks strength, cavitation resistance, and long-term seawater durability required for structural repair as compared to NAM. So we choose the nickel aluminum bronze, which does not have those, it's a weldable, easily weldable material, but we can repair, we can utilize that. So this is the wire we use. We scan the part, like I said, these are the cuts you see, very bad cuts. I mean, this is impossible to repair almost by manual labor. But again, if we do a robot task to, do that, we could manage. All this is path planning. I think I'm close to my deadline, right? Maybe I'll skip this conformal slicing. Like I said, in this case, you do not deposit layer by layer like this, but in a conformal fashion. Okay. Then we deposited, you see the video here. How much it is stopping, when to stop is all planned earlier through depositing a wall and tested its microstructure, mechanical properties, everything. That was very important. Later on, I'll show you the results. This is how deposited material looks like. Then we can grind it off. Wherever we see the defects again, we can again repair those locations particularly very quickly. This is the repair of that very long cut. This was the most, actually, this was most difficult, because when you keep depositing like this to overcome the, to regain the thickness was most difficult part because it was very thin. And if you deposit material on a thin blade, it will definitely warp, right? We have to avoid warping. So we planned the tool path in a way that it does not warp. So this is before and then after. Of course, this is the earlier when it was, you see the portion, it's literally gone, right? The thickness. And after that, we could deposit. Finally, there's a part we could grind it off and provide it to them. Some metallurgical analysis I'll show you. We deposited first. Of course, we took a broken part because they made a deliberate cut, like I said. We deposit material onto that. Did the testing. We find that the grains, of course, in the deposited part are quite smaller as compared to the base. And because the base one is the casted one, you see in detail the EBD for the same, the portion over here and the interface also, you can see the nice merge of the grain. Of course, there are not very small also, very sharp change as well was also not observed. As well as we perform and the texture shows the ABSD texture shows that quite random, colors available here. That means the orientation is quite mixed, not anywhere in any direction biased. Okay, we observed it on bead. Bead, when I said, is the deposited part at the interface and at the base. And of course, the base look different. And the reason is obvious, because it's a casted part, right? I mean, the base is casted. Strength, right? So we got quite good elongation. Of course, these are the 3 samples. They all broke from the center neck, and that shows that, okay, this is a good to go part. I mean, there are no defects into that. It was not breaking from the neck portion. And we see nice ductile fracture. Strength was low, of course, as compared to the elongation was low, actually. And we can obviously see the reason for that. But if required, we can provide the later on heat treatment. But this was acceptable to the my funding agency. Strength, of course, the distribution of the hardness. We see the deposited bead, there is a substrate, and it was quite homogeneous, right? Of course, low hardness in this zone. We saw some high hardness on the base side, maybe because of the heat affected, but this portion was quite with a homogeneous hardness in the deposited zone. After deposition, we scanned. This is the right view, this is the left view, I mean the front view and back view. There was no under deposition. Under deposition is blue. We see not very blue portion. Everything was mostly on the green. Correct? You see the distribution here. This is the green. That means some excess deposition, and this is the portion where we deposit, where it was very thin and we deposit extra material. We deposited deliberately extra because we need then a nice grinding guy who can do the grinding of that tip, which gives it right profile. So we didn't do that. But that gave us a new project. They want, because India doesn't make S-class propellers, as I came to know, and because we do most of the buffing by hand, we want to do it by robotic, because as our expertise lies in CAD or CAM, and we have robot which can handle the grinding as well. We are thinking, okay, let us use those robots, for grinding applications as well, even casted part, and implement all our CAM expertise into that to create very high surface roughness. Below 500 micron is, I think, they want. But currently we hand it over to them like this. They will do the remaining polishing of this. I mean, the further finish. This is the summary. Those are the cuts. Those were the cuts. You see here, those black line. This was the cut here. There was a long cut here, and this portion was anyway gone fully. We repaired, and these are the paths. I mean, this is called the path. This is a very interesting case of bearing cage, of course, where the challenge is how to make this 90-degree deposition without, any support. And we can do that. BAM is a process which can create, I think, very, very complicated parts, without any support. Some other cases of deposition, I'll skip those. This is an interesting 3D printing, again, DED process, but not with welding, with induction heating. Here, the induction heater is generating the heat, partially melting the deposition, as well as depositing the new bead. We are also working right now on putting some magnets, permanent magnets, in a way that it directs the induction heating. I mean, the what do you call, magnetic lines, in a way that towards the substrate, so it locally melt the substrate also. Work like a conical heat source. So we are working. We got some success. I'll come back to that later. But this requirement came from L&T. They said that, can you make rebars? Maybe very futuristic looks to you right now, but that could be the future, where you don't want to carry such rebars, right, like this in truck, but in the form of coil, and the robot itself can print on site. We printed. These are the rebars printed, tested on concrete. They have tested it. They provided feedback, and the bad surface finish you can provide deliberately. Why to have solid rebars? Why can't we have hollow rebars? Hollow rebars you can circulate water through. It can cool down the concrete. The same water can be reused. How much water we waste, you know that on construction industry. I mean, imagine all the rebars are hollow and connected. You supply heat, water from one end, circulate it through the entire building, and then collect back, cool it down, and then again supply. I mean, of course, very ambitious, but that that's our research part. But L&T was keen, and we had multiple rounds of discussions. And why to have straight circular, because all the rebars are made by continuous casting or then extrusion, of course. Getting it hollow is impossible. But we can definitely do that with 3D printing. So all these case studies must be motivating to you that what this robot is doing in the lab. It should come out. It should come out and work on the site. So we submitted proposal and still waiting few approvals on how do I make a mobile van. Mobile van means the robot is in a truck. It can go there. It can work there, and then it can come back. That's where it will work for offshore industry. I recently had a meeting with the Navy. There was a shaft. They have shown me very big shaft, around 500 diameter. It was worn out from between. They currently put FRP and temporarily repaired it. Imagine a robot would be there and then it would have just deposited that worn out portion. But I mean, of course, it would be definitely better than FRP, right? But there's a requirement now. Looks like we are also working on a project for GRSE Garden Reach, where we are making this turbine blade. Of course, these are 3D printed turbine blades just for testing. It's just a prototype, what you see. We are going to make a 1 meter tall, approximately 1 meter tall turbine, the whole helical turbine by 3D printing. I mean, by WireArc additive manufacturing. These are some trials. Of course, we are finalizing the shape because that doesn't work in this area. So we took the profile from the research papers, the profile of the blade, and we are testing whether the shape will be perfect or not. So we made a small setup, for testing. It looks like it's working. We are measuring the RPM, absolute RPM of in different orientations, trying to see the absolute value of those with velocity and then how many turbines to be put. So these are all 3D printed turbines, but plastic. We are going to use our robotic arm to build those large turbines, hopefully soon. We already procured the material, and with the help of GRSE, we are progressing on to that. I would like to add about a work we are doing at IIT Guwahati is called underwater welding. Underwater welding we don't do. It is being done at Cochin. Cochin has a nice facility with our partner where you can learn underwater welding, the certification program. Typically, till now in India, there was no indigenous underwater welding certification program. So we talked to IRS and we said that can we build a underwater welding course. I will do the testing. We failed. We took 3 years, 2 years for us to come up with a proper procedure of what they need to do at the diving facility. They will send the samples to me and then I'll test, and then we made the course curriculum in a way that they build appropriate samples, appropriate heat treatment, and then the mechanical testing can be done, and then they can pass. They can be certified. But I'll not certify. IRS will certify, and that's make a big difference because now these people and these students are eligible to do underwater welding, and not only in India. In India, I'm even finding it difficult because it's just been done, but they have a lot of requirement in other countries where it's mandated to show certificates from I mean these registers. I mean the class societies before diving and doing welding, right? So we got even very recently some interest. I'll show you. I'll skip this. We recently certified 7 more students. These are all very recently certified. We conduct a symposium on underwater welding, offshore repair, and additive manufacturing. And in this event, Iyengar sir also graced the occasion. Sonovalji, our honorable minister, has also joined the event and displayed our repaired propeller, as you see here in this image, and also motivate these students, provided them certificates that day. So this is like a second batch, but the largest one. Total 9 students have been, candidates have been certified by underwater welding, which is first of its kind in India. The right side, you see the propeller repair. We are now working with IRS to let us develop the guidelines for, repairing propellers through additive manufacturing and then provide these guidelines to the companies, those private industries, where they can further take it up. Maybe my lab can be certified. So we are working on those guidelines. So those are missing, and I'm very keen on such work because that add value on making a long way go for any of this kind of work. Instead, just we are doing and depositing and then giving it to them. IRS has kindly agreed, and we will update you soon on that. Other than that, on water, what we are doing, we also have, I request whoever possible, provide us next year a sponsorship. The event happens in September. We call it Aqua Wars, where we let the robot fight on lakes. Water body. It's not like Robo War where we make the robo fight on ground, but these robots are water robots and like a boat, and then they fight there. We conducted its second version this time, third version this time, and we have got 17 entries this year. Many from across the India are coming to IIT Guwahati. This is one of its kind in the world. Of course, RoboWar was there, but Aqua Wars was not there. Third time, 3 years consecutively we have done, and maybe we'll do it for a few more years. So, like I said, what we do at IIT Guwahati, we are good in this. So let me show you this video and add the slides. A video of dancing robot. Sound you may not be able to hear, but there's a nice sound also of a song of A.R. Rahman. But right now, you can just have a look at how we can make these robots dance, because that's what we do. We do path planning for 3D printing. So thank you very much, sir. I hope I haven't taken extra time. If I did, I'm sorry. Over to you. Thank you.
Thank you, Professor Kapil. It was an enlightening talk. So many details you have given. I will open the session for questions. There is one question from Mr. Kamal Palit. Would you like to bring him to the panel, or shall I read out the question?
I can add him to the panel, sir, from the
Yes,
background. Just a
yeah.
second. Yeah, Mr. Kamal Palit, you're in the panel. You can address your question, please.
Mr. Kamal?
Palit, you're online. You can just put your question. Or
Okay.
yeah, perhaps.
I'll read out the question.
Yeah, Mr. Palit. Yeah, I've seen your raised hand. Please. Yeah.
I think we're not able to hear Palit, sir. So maybe
it's okay, but I can read his comment,
Yeah.
what he said.
So he just wants to know how to weld and repair fractures on pillars, on offshore pillars.
I don't know what is offshore pillar. I'm sorry, I'm not from this background. So let me assume, let me search. This is the best part of online lecture.
Dr. Iyengar
And
can
let you-
clarify what is offshore pillars.
Please, sir. Underwater or outside water, I'm not sure. Now I can see it. It looks like on a column in which the whole rig and everything is mounted, right?
Yes,
Just correct me
that's
if I'm
correct.
wrong.
Yeah, that's correct.
So it's something like this, right?
Yeah, this is something like this. Yeah.
Yeah, if it is outside, yes, of course. It will be challenging. Now, then you are saying the robot should be on a boat, which allows it to, reach there. But yeah, it's very challenging. The bot will be, and this is a stationary item, bot will be on water. Difficult right now. I can't I don't think it will be easy, but of course, theoretically possible. Underwater repair I have not done any robotic repair till now underwater. All is manual, but certifying. I'm just certifying the human right now for we are certifying, not I, IRS, IIT Guwahati, and but not a machine which can do underwater repair on through additive manufacturing. I haven't done anything on that, but this will be challenging and interesting. I'll think about this.
Okay. Thank you. Dr. Ghosh Roy has raised his hand. Dr. Roy. Dr. Roy, you have a question? Okay, I will ask a question. When you are repairing these propellers and many other repair process you are doing, how do they certify that? Is there some non-DT, NDT evaluation, or how is it certified?
Yeah, thank you, sir, for asking this. So I that day, luckily, I was making a reactor. It was a reactor for some professor, and there was some work on welding. So I invited a guy for radiography test on that, and I used the same here. I asked the same guy, can you also check my propeller, which I repaired? So he found some defect in casting portion. Of course, because there will be, and of course, it has to be. Now it was very difficult for him to set the reference for casting and welding. So, but he could not find much of any of the defect of lack of fusion or crack developed by welding. So this is how you can do NDT of these propellers. But of course, we need to have. I think there I see a requirement of AI also, because I can check by radiography in future, and then ultrasonic test, of course, and then I can cut and see why those peaks were coming and train my network to correlate okay, these type of peaks are being seen because of that. So that is a nice research problem on NDT. But what we also do, we deposit before depositing onto the main part, we take a portion of that, deposit material, build wall, and do entire testing on that, and destructive testing. So we did that. All those results you saw, sir, on tensile, as well as the microstructure variation from base, everything we did separately. We took a portion of that.
Yeah.
But if there can be a machine of CT scan, but I know it's a huge part, but that would be like the best.
Yeah.
But very theoretical answer, right?
Yeah, because there are no known protocols for additive manufactured parts. It's still being evolved. That's why I was asking that question. Anybody
Yes,
else has question? So there's some good feedback from people.
Thank you so much. So definitely, I would also like to add, if the student, I mean, if they are, I don't know their background, but if they want to learn more about additive manufacturing, there is a course on NPTEL, which is called as Fundamentals of Additive Manufacturing. Of course, now it will start next semester, but the lectures are available on YouTube. Whoever interested may definitely watch it. Thank you.
Okay. Does anybody else have any question? Okay, if there are no questions, I would congratulate you for an excellent lecture. I'll just summarize this lecture.
So before the summary, I would request if the chief guest can give his comments, sir.
Yeah.
You can just give his comments.
So very good morning. Good evening to one and all present here. Actually, this area of WireArc additive manufacturing is a tool for manufacturing components, products, and for repair of the small components. And I hope this topic is very relevant as far as the industry is concerned. Are you able to hear?
We are able to hear you. We are able to hear you. Please go ahead.
Yes, sir. Yes, sir. Yes, sir. So since the evolution of a human being, we have been developing welding processes, various type of welding processes. The first process was the forge welding. Then onwards, we have developed so many processes, and this would be an added advantage for developing new components, new products, and for repair of the products or the components which are used in the marine industries. Though it is not used for making of large, structure or large type of the components, but for the small components can be used. There are a lot of advantages also in this process. For example, if you take the design freedom, as the speaker pointed out rightly, the complex components can be easily manufactured, and you have a less cost also for this manufacturing. Is it so?
Yes, because anyway it was a waste. So yes, yes.
And also, the materials choice also very relevant. So compatibility of materials also very important. And also we can go for a hybrid manufacturing. We can connect this process with any other process. Also, the waste reduction is very less. I am sure the waste reduction, which is of sustainable
Yes.
production process. So in a
Yes.
way, it is very good process. And as far as mechanical properties or corrosion resistance properties are concerned, I am an expert in corrosion engineering. So if you need any help in the analysis of corrosion aspect, you are welcome. And most often, this process are used in many industries in abroad. I hope in future this will also be adopted in Indian industries. And the processing difficulties, that is what you mentioned, no? Post processing. You said some heat treatment and all, no? How the heat treatment is going to affect, what are the mechanical or the metallurgical properties? Those things also being studied. So that will be area of interest. In fact, just I want to know the process and details. In fact, I would like to contact you in future. But we are doing a lot of work on welding, but not into this additive manufacturing. So far, we have instrument, but not for the industrial applications. Small components we are able to manufacture, but not very large components. And very interesting point you mentioned that propeller repair. Propeller repair, no, it is very interesting area as far as the shipbuilding industry is concerned. Even for the shaft, you mentioned. So I hope that future will continue to support Indian maritime industry, and we will look forward to hear and develop new products, new design, a new kind of the process and the computer aided support also in this respect. Thank you for your presentation, and also make ourselves enlightened in this area. Thank you very much.
Thank you. Thank you.
Thank you, Dr. Mathiazhagan. He has nicely summarized, and we can see that there are several opportunities in this area, both from the production side, and there is a lot of things to do on the science side also. If there are no other remarks or question, anybody has any remarks to make? Okay, so I will summarize the proceedings. First of all, I should thank Dr. Iyengar, Dr. Mathiazhagan, and Dr. Sajan Kapil for an excellent lecture. He always connected with nature, and whether it be the initial describing additive manufacturing process or functionally graded materials. So he connected with nature, that is very nice. And he started off with different ways of additive manufacturing, Then he went into DED process. Then the importance of tool path he brought in. And the spiral build path he explained with Jalebi, that is very, very interesting. And it's also an ingenious way of choosing the tool path. Also solves the problem of heat treatment. That is very, very, very important. And controlling porosity is also very good. He was able to make the controlled porosity objects, which will have some application like boots or something for defense people. Then the functionally graded materials, he started off with composition graduation, and he has shown with 2 wires, maybe it is possible to do with multiple materials also. And he also discussed several case studies of impeller and bracket for aerospace industries. Then MMCs of firing pin with the tungsten fiber, then turbine blades, then stone crusher, jaw, etc. And I could see that there are several advantages of this process. You are able to do in any path that you can imagine, but there are several challenges also. So thank you very much, Dr. Kapil, for a wonderful lecture. Over to you, Dr. Iyengar.
Thank you, sir. Before I close the proceedings with the formal vote of thanks, I would request if the President of ANA, Dr. Manukurla, wants to add something before closing, sir.
Thank you, Dr. Bharadwaj. Actually, it has been a wonderful talk by Professor Sajan Kapil. And this topic is very important because many areas people are attempting now for using additive manufacturing. And the niche areas like even for getting the aero engine realized, now probably we may have to depend upon additive manufacturing, but it has to improve a great deal. I really thank Professor Sajan Kapil for this wonderful work. And now if this platform, if it has given a way for synergizing the effort that you are doing, then I think we are successful. I really appreciate Dr. Sankarasubramanian for a wonderful moderation. And I really thank Professor Mathiazhagan to be the chief guest for this wonderful program of today. I also thank each and every one of INA, including the people who have made it possible today, Amir Ahmad. Though I'm not thinking that I should be giving a Thanksgiving speech, but I feel that this should be known with people having a lot of work in the last month of the year. People are at different places. I can understand where Bharadwaj Srinivasan must be sitting now and participating. Like that, each and every one of you, has made real tough, efforts to participate in this program. But this is a new paradigm shift, the way we have to look at manufacturing. Professor Sajan Kapil has brought in many other areas, and where all we could apply this philosophy. He has also brought in the underwater repair. Anyway, it is also we all should know that DRDO also to a great extent working in these areas, and there can be a lot of support from DRDO as well, for work in these areas. Now, being Bharadwaj being NRB secretary, Naval Research Board secretary, he'll also be able to make a lot of effort in bringing together different institutions and to have a concentrated work in this area. Once again, I congratulate. Greetings from INA for all the participants and all the members for the coming Christmas and New Year. we are going to have a journal release. I hope Dr. Bharadwaj will again briefly, give some details of that as well. Over to Bharadwaj.
Thank you, sir. Before the formal vote of thanks, as President was mentioning, INA has a journal which we are publishing annually, which will increase the frequency slowly. The edition for 2025 will be released by this year end, and probably we'll be having one more session to do the formal release, and it will be available in the INA website for reference. And in future also, papers are welcome to be published through the INA journal. Having said that, and Dr. Raju Sharma, Professor Raju Sharma of IIT Madras is the editor of the journal, and he takes care of the publication of the journal and its logistics. With that, now I'll just come to the last part of today's basically vote of thanks, and Dr. Manukorla has already mentioned some of the things, but yes, my first thanks is to Dr. Mathiazhagan for accepting our invitation to be the chief guest and offering his views. I know him since 30 years when I was a student, and he was my teacher, and so he taught welding to me. And if I know something about welding, it was because of the first lessons which Dr. Mathiazhagan taught us. And from there, of course, we learned from the industry. And thanks for accepting my invitation, sir, and coming and joining as chief guest. My thanks to Dr. Sankarasubramanian. When I contacted him, he gracefully accepted to be the session chair and has moderated the session excellently. He is from a lab which is primarily working on materials, and so his expertise also fitted the session. And thanks for joining us, sir, and moderating the session excellently. And Dr. Sajan Kapil, we had even probably 1 month back, roughly 1 month back, and I was impressed about the work in IIT Guwahati. And then the next day, I just called him and told, "Can you give this talk?" And I know he was busy. He had another event today, and probably he came back to Guwahati at around 3 o'clock, as Dr. Manukorla was mentioning. We had enough events and enough these things, but still, thanks, sir. Thanks for joining, and thanks for sharing the knowledge to a wider audience. It was indeed informative. Dr. Manukorla, he has been behind all these events as President INA, and ensuring that the INA runs properly and these webinar series are continuously happening. And Amir, Selvi, Mr. Chandan Maiti, and all those who are behind to have this very smoothly and these events happening. Thank you all. And as Dr. Manukorla has told, we'll be releasing the INA journal as well. I also want to thank around 20 participants, all very senior people. Mr. Kamal Palit was had extensive experience in the previous president of INA, Shipping Corporation of India, and before that, the industry and GRSC. So we had Mr. Kalgatki, who was appreciated, who was a very senior IR surveyor before retirement. We had very senior participants who have spent probably collectively 30 or 40 years in the field individually or even higher to have appreciated and this topic because they know what it is to take it to the field. Thank you all for joining.
Admiral Nirmal Menon also I have seen. He was also
Nirmal Menon also. So we had a good participation from very experienced people who had all joined and listened to us, and probably in future also guide us. With this, and wishing all a happy Christmas, happy New Year. Goodbye, and thank you all for joining.
Thank you.
Okay. Thank you, everyone. Bye.
Bye. Bye. Thank you. And Amir, you can just close the session. Yeah.
Yes, sir, I'll do that. Yeah. Thank you.